Hello everyone. So in this video we will continue our discussions on free radical halogenation of methane, and specifically what we're going to do is we're going to dwell into some of the thermodynamic aspects of this reaction. So what we've seen earlier in a previous video is that the mechanism of free radical halogenation of methane, and when we say free radical halogenation of methane, we are talking about this reaction where methane reacts with chlorine, okay, in presence of heat or light to give methyl chloride plus HCl. HCl. So that's the reaction that we're focusing on. And so last class, or in the last video, we actually worked through the mechanism, and I just want to go over the mechanism again quickly before we jump into the thermodynamic aspects. So the reaction starts with an initiation step, and the initiation step here involves the chlorine molecule. So the chlorine molecule uses light, or it could be heat, so basically some sort of energy, to break homolytically. So the bond breaks homolytically and it produces two chlorine radicals. Since this is homolytic bond cleavage, we're using these fish hook arrows or the single-headed arrows because we're showing movement of one electron. Now, that's the initiation step. So what happens in initiation step is that radicals, which are our reactive intermediate in this mechanism, are produced. So that's how the reaction gets initiated. If there are no radicals formed, then this reaction would not happen. So initiation basically results in the formation of those radicals. That's why we call it the initiation step. Now, subsequent to initiation, we have propagation steps. What happens in the first propagation step here, so this is the first propagation step, and then we have a second propagation step, is that I'm going to remove those dots so that does not cause any confusion. The chlorine radical, okay, it uses its one electron and it reacts with a molecule of methane. And methane, again, it breaks one of the carbon-hydrogen bonds homolytically to produce HCl. So the chlorine brings its one electron, the bond breaks, hydrogen brings its electron to combine with chlorine, that gives us HCl. The other electron in this bond goes to carbon and we get a methyl radical. So, and this is a propagation step. So an easy way to identify a propagation step is to look for the reactive intermediate. And a propagation step is one where the reactive intermediate is regenerated in some sense. Okay, that means it's there on the reactant side and it's there on the product side. So if you look at this step here, we have a reactive intermediate, which is the chlorine radical on the reactant end. So there is chlorine radical here. And we have another radical on the product end. It's not the same reactive intermediate, that doesn't matter, but our reactive intermediate, well, I guess technically it's the same because it is a radical, but it's not the same entity per se. So it does not have to be a chlorine radical. It's a methyl radical, but it's a radical. So that means it's something reactive. It can basically go ahead and do other stuff. So that's how you identify a propagation step. The reactive intermediate should be there on the reactant side, and it should be there on the product side. So we make methyl radical. Then the methyl radical reacts with another molecule of chlorine, brings an electron. The chlorine breaks homolytically. One chlorine goes with the methyl radical to give us methyl chloride, CH3Cl, and we make chlorine radical again. So notice how in this step, again, we have a reactive intermediate, a radical on the reactant side. So that's a radical. Plus we have a radical on the product side. So we basically regenerate our reactive intermediate. So that's also another propagation step. And from our discussion last in the previous video, remember that this is the step where products are formed. Okay, so products are formed in this step. Okay, now beyond this, towards the end of the reaction, we have termination events. Now, these are all termination events. Now, how does a termination event differ from an initiation or a propagation? So again, recollect that initiation is where our reactive intermediates are formed. Okay, we don't have any reactive intermediate on the reactant side. On the product side, we have reactive intermediates. Propagation steps, there's a reactive intermediate on the reactant side, and there's a reactive intermediate on the product side. Reactive intermediate on the reactant side, reactive intermediate on the product side. So it is regenerated. Termination steps, these are different from both of these because there are reactive intermediates on the reactant side, but there's no reactive intermediate on the product side. That means the reaction cannot continue now. It's going to basically end. If this step happens, the reaction must come to an end slowly. So a methyl radical, like of the reactive intermediates that we have in this reaction, okay, our possibilities are a methyl radical. It could combine with a chlorine radical to give us methyl chloride, which would be our product. A methyl radical could combine with another methyl radical, combine in the sense react, okay, and then give us ethane, CH3CH3. Or a chlorine radical can interact with another chlorine radical, react with another chlorine radical to give us Cl2 back. So in all of these cases, we have radicals on the reactant side, but on the product side, we have molecules. There are no radicals. There are no reactive intermediates. So these are all termination steps because when this happens, the reaction is basically going to stop. Okay, so that's the mechanism. Now, of all these steps, the most important steps are the propagation steps because these are the ones, these steps result in the formation of the products. Okay, the initiation step happens in the beginning of the reaction. Termination steps happen in the end, like towards the real end of the reaction, when there isn't a lot of reactants around. But there aren't a lot of reactants around. The propagation steps, these happen during the bulk of the reaction, okay, between when the reaction starts and when the reaction ends. So throughout that period, the propagation steps are going on. And these are the steps that are thermodynamically important in the sense that they contribute to the delta H of the reaction. Or let's say if it's entropy, these are the ones that are going to in fact, thermodynamic and kinetic, in general, again, mostly the thermodynamic and the kinetic parameters, I would say at least in this case, there could be cases, again, when things are going on. I would say mostly thermodynamic. Let's keep, I think because kinetic, there could be other issues, but thermodynamics of the reaction are mostly controlled by the propagation steps. So what we're going to do in this video is actually do thermodynamic calculations, and we'll try to come up with a reaction profile diagram for this chlorination of methane. So whatever we learned in chapter 6, we're going to actually build a profile like that. Now, since termination steps not important, I'm going to erase this part because we don't really need this for our thermodynamic discussion here, and I will use this space for doing the rest of the work. But before we get started, we'll do the thermodynamic calculations. Now, in the Wade's textbook that we are the Klein's textbook that we are using, the bond dissociation enthalpy parameters or the values can be found in table 6.1. Okay, that's the table where everything is present. But I'm going to use the values from a different textbook, which is the Wade's textbook. And I will post that table on Blackboard. So then you will have access to the table. Okay, so based on the Wade's textbook, now I can, or based on this bond dissociation enthalpy table, I can find the bond dissociation enthalpy for each of these bonds. So if I look at the first propagation step, I'm breaking a methyl hydrogen bond. So I can go to the table and I can actually look for what or how much energy is needed to break that bond, or what's the bond dissociation enthalpy for that. So based on the table, the energy required, or the bond dissociation enthalpy, uh, not energy required. Okay, I think I talk in terms of bond dissociation enthalpy, because then that would help me point something else out. So the bond dissociation enthalpy for a methyl hydrogen bond is 439 kilojoules per mole. Okay, so it's 439, the bond dissociation enthalpy for a methyl hydrogen. So please take some time, once I post this, go through the table and make yourselves comfortable looking at the table and getting a value from the table. Let's say if you have to pick something, what's the bond dissociation enthalpy for a methyl bond? Let's say if you wanted to find something like that, should be comfortable enough to go into the table and basically extract that value out, to dig that information out. Okay, so we are breaking a methyl hydrogen bond. Bond dissociation enthalpy is 439 kilojoules per mole. And we have, on the product side, we have HCl. Now the bond dissociation enthalpy for HCl is 432. In the table, I'll see this number 432 kilojoules per mole. But that's the bond dissociation enthalpy, which means it's the energy required to break this bond. But in this particular equation, HCl is on the product side. That means this is a bond that formed. Okay, so because of that reason, if the bond dissociation enthalpy in the table is 432 kilojoules per mole, the bond formation enthalpy should be the opposite in magnitude. So essentially it's going to be negative 432 kilojoules per mole. Okay, so that's the bond formation enthalpy right now, not the bond dissociation. The bond dissociation enthalpy is 432, but the bond formation enthalpy is negative 432. And now that I have these two numbers, all I have to do is, for delta H, for this first step, is, okay, I think I need a little bit more space. So delta H for that first propagation step is basically 439 plus minus 432, which is basically 7 kilojoules per mole. Okay, so it's basically a sum of those two, since we've already converted the bond dissociation enthalpy into a bond formation enthalpy. Okay, if you do not, then you're going to subtract it. Either way, so it is 7 kilojoules per mole. And what that number is telling me, it is a positive 7 kilojoules per mole. That means for this step, more energy is required to break the bonds than the energy that's released when a bond is formed. Because again, remember, bond breaking requires energy. Bond formation releases energy. So that's why this is a negative number. But more energy is required, and this positive value of delta H for the first propagation step means that this step is endothermic. That's the information that I'm getting out here. Okay, now we'll go to the next step now. Sorry, in the first step now, I do not have to consider this chlorine radical because there is no bond being broken there. It's a radical, so I cannot come up with an energy for that, or a bond dissociation enthalpy for that. Do not have to consider the methyl radical because that's not breaking a bond. The bond's breaking here, and we have the number for the formation of methyl radical from that enthalpy. Okay, now for the second propagation step here, we don't need a number for the methyl radical, but we need the enthalpy for the chlorine. And This number for Cl2 from that table is 240 kilojoules per mole. 240 kilojoules per mole. On the product side, we are making a methyl chlorine bond, and the energy that's released here is negative 350 kilojoules per mole. So in the table, the bond dissociation enthalpy for a methyl chlorine, you should find the number 350, but that's bond dissociation enthalpy, and since we are forming a bond, I've put negative to it because that much energy must be released. So that's the bond formation enthalpy for the methyl chloride. And again, we can go ahead and calculate delta H for this second propagation step. And this is 240 plus minus 350, which is a negative 110 kilojoules per mole. And what that means is that the second propagation step here is it's a highly exothermic process compared to that endothermic step we had. Okay, we are releasing about more than 100 kilojoules per mole. So it's a negative 110 kilojoules per mole. Okay, so that's the thermodynamic calculation. Now, if we wanted to calculate the delta H for the overall reaction, okay, so delta H overall is basically the sum of these two. So this is 7 plus negative 110, which is negative 107 kilojoules per mole. So that's the delta H, negative 103 kilojoules per mole. So that's the delta H for the two steps combined. And again, going back to what I was saying earlier, since the bulk of the products are formed in these two steps, methyl chloride and HCl, this is the delta H for the overall reaction. Okay, now that we have the delta H values and the propagation steps are the more important steps, we can actually go ahead and build a reaction profile diagram for these two steps. How would that look? So let's go ahead and construct a reaction profile diagram. Okay, so I'll make it a little bigger just in case I run out of room. Okay, so let's say this is the energy scale. Now in this particular case, it's going to be enthalpy, the bond dissociation enthalpy, or the delta H is what I'm talking about. And here is the reaction coordinate on the x-axis. The y-axis is the delta H, or enthalpy. Yeah, energy is fine. I think it's just an energy, form of energy, so we can just use energy. And we have delta H on this side. So now if I look at this, and if we assume that arbitrarily, I'm going to assume that chlorine radical and methane are at this level. This is where chlorine radical plus methane are the reactants for the first propagation step. Now, the first propagation step we calculated is an endothermic step. That means the products from the first propagation step must be at a higher energy compared to the reactants because this step is endothermic. And so the products here, HCl plus methyl radical, are here. Okay, now HCl is actually a product. The methyl radical is an intermediate because Methyl radical is what continues from the first propagation step to the second propagation step. So that's the bridge between the two steps in some sense, okay? Because it's the product from the first propagation step and it's a reactant for the second propagation step. That's what connects the two. So this is endothermic. So that means when we do a reaction profile, these two should go up a hill, okay, through a transition state. Okay, there must be a transition state and they end up here. And what our math is telling us here is that this difference between the product and the reactant, this is 7 kilojoules. Okay, that's this number, 7 kilojoules. That's the delta H. Okay, now that's the first propagation step. Now we come to the second propagation step. And what happens in the second propagation step is the methyl radical reacts with chlorine. Okay, so we can include the chlorine here because the HCl is the product, and essentially we have chlorine in this point also, or at this point also. The methyl radical is now going to react with chlorine, and it's going to give us methyl chloride and chlorine radical. That step is exothermic by negative 110 kilojoules per mole. So if that step is exothermic, that means the products from that step are like way down here. Now, this is all, I don't think it's even relative, but I'm just trying to like draw a picture, you know. It's definitely not to scale. I mean, this, if this is 7 kilojoules, that cannot be 110 kilojoules, okay? So it's not drawn to scale, but over here, we get our methyl chloride plus chlorine radical. Those are products. And so now again, from here, what must happen is this should go up and then go down to that product. So that's pretty much what our profile should look like. We start with the first propagation, the reactants on the first propagation step. We get to the methyl radical, which realize that this now here is our, okay, I don't think I have, I'm going to actually erase the Cl and the HCl because those are products or reactants. Don't have to keep those here. Those are important, but I'm just going to erase to make some space for myself. This methyl radical here, this is our intermediate in this reaction. That's the intermediate. I know this is too small. I can see it on my screen, but that's the intermediate. Okay, this is I. That's the intermediate for this reaction. Okay, and then again, this difference here between the intermediate and the product, this is negative 110 kilojoules. Okay, that's the negative 110 because that's the delta H for the second propagation step. And if we look at the difference between reactants, this is where the reactants are, and the final product from both propagation steps, this difference is negative 103 kilojoules. Okay, that's the negative 103 that we calculated. So this is a reaction profile diagram for chlorination of methane, where we've captured some of this thermodynamic information and we could actually construct a reaction profile diagram based on those, based on that thermodynamic information. Now, I want to show you one more thing before we end this video, which is the transition state, some discussion about the transition state. I'm going to erase some part here because we don't need that now. Okay, now, so this is a two-step process. That's exactly what we had. We had two propagation steps. We have one step, and then we have another step over there. This is our first transition state. That's our second transition state. So transition states are represented by this dagger sign. So this is our first transition state, that's the second transition state. Now going back to chapter 6, recollect that transition states, okay, we cannot see those. They're basically presumed or hypothesized structures which give us some insight about what might be happening in a reaction. And we can come up with a structure for the transition state, okay? And the profile, the reaction profile, gives us some information about the structure of the transition state itself. So if we look at this reaction profile here, this is an endothermic reaction, which means the transition state is closer in energy to our product. So the transition state should look more like our product. Okay, so the transition state should have a lot of resemblance to the product itself. Is that good? Yes. So we can actually draw the structure of the transition state. Okay, that would help us draw the structure of the transition state. So those are our transition states, and in this particular case, since the first propagation step involves the reaction between a chlorine radical and the methane molecule here, we can go ahead and then draw the structure of the transition state. Let me just confirm something quick. Yeah, so we can go ahead and draw the structure of the transition state here. Okay, and since it's a reaction between the chlorine and the methane molecule, we can draw the transition state here as chlorine reacting with methane. Now, what's happening in this first propagation step is we are forming a bond between the chlorine and the hydrogen, and we are breaking the bond between the hydrogen and the carbon. So we can show those using dotted bonds or dotted lines, basically, okay? Because we're trying to form a bond and we're trying to break the other bond. So we can draw it using, we can show it using dotted bonds, something like this. And usually transition states are put in square brackets with this dagger sign to say that it's a transition state. Okay, but if I look at this transition state, the hydrogen here is almost equidistant or at the same sort of a separation from the carbon and the chlorine, which would imply that the hydrogen is like halfway between the carbon and the chlorine. That means this bond is forming, or it has formed to the same extent as the other bond has broken. But this reaction profile here tells us that the structure of the transition state, because it's an endothermic step, the structure of the transition state should be closer in energy to our product. No, sorry, not closer in energy. The structure of the, since the energy of the transition state is closer in energy to the product, the structure of the transition state must resemble products, should be more like the product. Okay, but this is implying that the hydrogen is somewhere in the middle. And if you look at the products here, we have HCl and we have methyl radical. That means the bond between hydrogen and chlorine has formed completely. The bond between hydrogen and the carbon has broken completely. So to capture that, what we're going to do is we're going to adjust this a little bit, where we're going to place this hydrogen closer to the chlorine to say that this bond has formed significantly, and this bond has broken significantly. That is what these distances are supposed to imply. Okay, or that's how we interpret those distances when we see something like that, that this bond has significantly formed and this bond has significantly broken. And that is true here because this is an endothermic step. The transition state is closer in energy to our products, which means it should resemble our products more. And in the product, we have a bond between HCl, H and Cl, and we've broken the bond between the carbon and the hydrogen. And overall, since there is a radical on the reactant side and a radical on the product side, we're going to put a radical outside the square bracket to say that this transition state overall has a radical character. So that's the transition state for this first propagation step. What I would encourage you to do is actually try drawing a transition state for the second propagation step. And I'm going to put it here, but I will not discuss it. And I want you to think about it a little bit and rationalize if the transition state that I've drawn makes sense. So I think the transition state for the second propagation step, which is when the methyl radical reacts with the chlorine, and it's an exothermic step. So I think that transition state should look like this. I think that's the transition state for the second propagation step. So we're going to finish right here. So essentially what we've done is we use the free radical halogenation of methane. We've developed the thermodynamic model for it, essentially, in some sense. We worked through the thermodynamic parameters of the reaction delta H specifically, and then we use those thermodynamic parameters to actually construct a reaction profile diagram, and we discussed the transition states, the structure of the transition state, what delta H are, things like that. The only other parameter that I did not point out here is the activation energy, which is the difference in energy between the reactants and the transition state. So this is a two-step reaction, should have two activation energies. So this is EA1, and this here is EA2. That's the second activation energy. So there should be two activation energies. So we'll stop right there. In the next video, we're going to develop this concept more, but apply it to another molecule and see how this applies to a molecule which has more hydrogens. What can we learn from that system? Thank you.